All right, so let's jump into lessons 10.4 and 10.5. We're going to continue solving systems of equations. And in these lessons, we're going to look at using elimination and then something called linear combination. So the big idea is the sum of the left sides of two equations, so the sum means adding them together, equals the sum of the right sides of those equations. So if I add the left sides and I add the right sides, they're going to still be equal to each other. So that's a property that's true that we can use to actually solve some of these in a lot faster and more efficient way than trying to either put these on a graph, which we learned in 10.1, or trying to get x or y by themselves so that we can use substitution like we did in 10.2 and 10.3. Okay, so we're going to jump right in. If we add everything on the left side and we add everything on the right side, they are still equal to each other. So it's a property that allows us to do this. So if I add them, I get 11x. And I add these, I get 0. And if I add these, I get negative 55. So since I get 0, I'm not going to write it. Now take a look at what I've created. Basically, these canceled because negative 3 plus positive 3 is 0. And so I've created a very easy equation to solve. And so you can see why this could be an extremely useful tool when we want to solve a system of equations. This looks like two kind of complicated equations, and we've made it very simple very quickly. So to finish this off, I would just divide by 11, and I've got my answer of negative 5 for x. Just like we have been doing, once we have this, we're going to go back and we're going to plug it in to either one of those equations, and we can go ahead and find the y, because remember, the solution is always an x and a y. All right, so if I go back and plug it in, it does not matter which one I choose. Either one is fine. So I'm just going to choose the first one. So it's going to be 4, and then instead of x, I'm going to put negative 5. Bring down the rest. And all I got to do is solve this now for y. So negative 20. Trying to get y by itself, so I'm going to add 20. When I combine that, I get negative 30. And so when I divide by negative 3, y equals 10. And therefore, I have one solution. And I state it as an ordered pair, x first, then y. So negative 5 and 10. Okay, so that's your basic elimination right there. Now that worked out because we had a negative 3 and a positive 3 as coefficients for the y's. Okay, if we don't have that, then we have to make some changes to them so that we end up with something that eliminates like that. So if you look at the second one, before you start adding them, we need to create something that's going to eliminate, because if we did just add them, we'd get 6x and 10y, and then a number over here, 60, and we would still have an x and a y, and you can't solve for either one if you have both of them there. So if you look back, these canceled because one was negative and one was positive. This looks like we have something that's going to cancel because you have a 3 in both spots, but when you add them, you get 6. Okay, so we need to make one of them negative. We have talked about that you can multiply an entire equation, and it doesn't change its properties. It doesn't change the equivalency. So what we're going to do is we're going to multiply this by negative 1 and get a brand new equation that's equivalent to this. Okay, but now we'll cancel very nicely with the first one. So why are we doing this? Let me show you. So I'm going to bring down the first one. And now as long as I multiply all of this equation by the same number, I have an equivalent equation. I haven't changed it in essence. And so the reason I did this is because now when I do multiply, I get a negative 3x, which if I add these equations together, will cancel. So when I go ahead and multiply here, I get negative y. And when I multiply here, I get positive 15. I'm set up now so that these will cancel. I get 8y. And I get 90. Divide by 8. It doesn't go in perfectly, but not a bad decimal. 11.25. Once we got this far, it's just like all these other ones we've been doing. You're going to go back, you're going to plug in your y, and you're going to find your x. I'm going to go to the second one because y is by itself, so I don't have to multiply by anything. But again, either one will work. So 3x plus, instead of y, I'm going to plug in 11.25, and it equals negative 15. All right, now I just got to solve this for x. So I'm going to get rid of this. So 3x equals, that's negative 26.25, divide by 3. And x equals negative 8.75. So I have one solution. I'm going to list it as an ordered pair with the x first. So negative 8.75 and 11.25. Okay, so that one, it wasn't set up perfectly, but it was close. All we had to do was change this 3 to a negative 3, and it was ready to cancel. So when we look at this third one, we don't have anything set up that nicely. We got a 3 and a 4 and a 2 and a 5. So what we need to do is multiply both equations so that we have numbers that will cancel. So you could work with the 2 and the 5. It's basically like finding common denominators. You're going to multiply them by each other, and you'd end up with 10s on both sides. But a 10 and a 10 won't cancel, just like a 3 and a 3 wouldn't cancel. So you'd actually want to multiply one of them by the negative version so that you had a negative 10 and a positive 10. But that would work. But if we come here, we've already got a negative and a positive, so we don't even have to mess with signs. We just need the numbers themselves to match. So just like if I was going to find a common denominator between fractions that had a 3 and a 4 on the bottom, I'm going to multiply by each other and create 12s. So I'm going to multiply this top one by 4. I'm going to multiply this bottom one by 3. Why? Because when I multiply this one, I get negative 12x. And when I multiply this one, I'm going to get positive 12x. And those are going to cancel. So that was the whole point of that. I chose numbers that when I multiply, I'm going to get matching numbers. One's positive, one's negative. So they will cancel just like these first two examples. So if I continue, make sure you multiply everything by 4. Otherwise, you've changed the equation. Okay, so I'm going to get plus 8y equals 24. And on the bottom, I'm timesing everything by 3. So I get positive 15y, negative 93. So 23y, negative 69, divide by 23. And y equals negative 3. So that's the hard part. And now I just go back and choose either one of those equations and plug this answer in. So I'm going to go to the first one. And when I get to y, I'm going to change it to negative 3. So negative 3x minus 6 equals 6. This was a negative 6, so I wrote it as minus 6. Add it to get rid of it. And divide. And I get negative 4. And so I've got one solution once again. X first, so negative 4, negative 3. So as you look at these three examples, the first one, we just added straight down because it already had opposites as coefficients, so they would cancel. The second one, we couldn't do it right away, but we had matching numbers, so we just multiplied by negative 1. So now they were opposites and they could cancel. And on the third one, we did not have anything that was set up to cancel. Even if we multiplied by a negative, it still wouldn't cancel. And so we multiplied both equations by something to create opposite coefficients to cancel. Sometimes we will need to multiply by something other than negative 1, but we only need to do it to one of the equations, not both. We'll take a look at that here on the back. So if you flip it over, this first one is that kind of example I was just talking about. So if you look at these, we don't have anything matching. We don't have anything that even if we multiply by negative 1 is going to cancel. But I can turn a 5 into a 10 very easily. And I don't just need a 10, I need a negative 10. So I can multiply this first equation by negative 2, and I will create something that's going to cancel. So I don't need to multiply both equations in this case. So I wanted to show you that you don't always have to multiply both of them if you don't have something that matches. So this top equation becomes negative 10x, negative or minus 16y, and negative 42. And if I go ahead and drop the other one right underneath of it, I'm all set to cancel. So the negative 10 and the positive 10 go away. That's why I multiplied by negative 2. I'm going to get negative 19y, negative 57 here, and that will divide nicely, and y is 3. So I just wanted to show you that you don't always have to multiply both. Okay, you decide how you want to do it. You could have multiplied both of them and canceled the y's. You could have multiplied them by 8 and 3 each other and gotten 24 and negative 24, and that'll cancel. But I think it's easier, if you can find it, to just multiply the top one by negative 2. All right, so we've got y. Let's go back and plug it in. I'm just going to grab the first equation. It doesn't matter. 8 times the y value of 3. And now I just need to solve this. So that's 24. So 5x equals negative 3. Divide by 5. Now that's not going to work out perfectly. So x equals negative 3/5. Or if you wanted to turn it to a decimal, it's a decent decimal. Negative 0.6. And so we have one solution listed as an ordered pair. X first. I'll go ahead and put the decimal. Doesn't matter though. You could put the fraction. And the y value is 3. Okay, so that was one of those that you only had to multiply one of them. Now we haven't talked about our special cases. So let's run through these last two so we can talk about our infinite solutions and our no solutions. What's that going to look like? Now, first of all, when I take a look at these and I want to use elimination or linear combination in order to solve this, I don't have anything set up to cancel yet. What's nice, though, is these coefficients are 1 and negative 1, and so it's very easy to multiply them and create something that's going to cancel here. So since this one's already negative, I know it'll cancel with this if I just times it by 3, because that would create a negative 3, and that'll cancel. So if I bring it down here, I'm going to get negative 3x, I'm going to get positive 3y, and I'm going to get positive 15. And then I'm going to bring the other one down right underneath of it. And take a look at what happens. So, of course, these cancel. That's what I was trying to do. But now these canceled too. So when I add up the entire left side, everything cancels. So that's 0. And on the right side, 15 plus negative 15 also equals 0. So if you take a look at that, 0 equals 0 is a true statement. Okay? So that means this is our example of infinite solutions. We've already talked about how this comes about. If you put these on the graph, you'd have a line going one direction and you'd have another line right on top of it. And anywhere you go on those two lines, any of those points are going to be solutions for both equations. So because those lines go on forever, there's an infinite number of solutions. Now the last one, of course, will be our example of no solution. What does that look like? So first of all, when I go to start trying to use linear combination here, I'm going to have to multiply one of them. I don't need to multiply both of them. I can just multiply one of them to create the other. So I see a 4. I can turn it to a negative 12 to cancel. I've got a negative 2. I could turn it to a positive 6 pretty easily. I'm going to go over here and just deal with the 4. And so since I want it to be a negative 12 to cancel with the positive 12 here, I'm going to multiply by negative 3. So let's see what happens. I'm going to bring this down. And I'm going to multiply this one. So I get negative 12x. I'm going to get a positive 6y. And I'm going to get a positive 9. So don't forget to multiply that last part. It's important. These will cancel. That's what I was trying to do in the first place. But now these will cancel as well. So when everything cancels, it's 0. But this time the right side will not cancel, because when you put those together, you get 6. And I'm left with the statement that 0 equals 6, which we all know is not true. And so this is a case of there being no solution. And we talked about what that would look like on a graph. These two lines are going to run parallel to each other. They're going to have the same slope, and they're never going to cross. And so there's never going to be a point that solves for both of them.